That makes sense. Or maybe two.
Because then it's like the opposite.
You didn't have to. Oh, from the I don't know the flying they are not sure. Anyway, just yeah. Maybe it's the other one might higher. Yeah, I barely got that out. It's like, huh?
The only way I know
Alright class, we should start. Welcome back after the break, or rather welcome to the second half of the semester. Hope all of you had a good and refreshing break and are ready for more. I was doing that in the break. We'll get to that at the end of the class. Some interesting events happening this week. There's the first talk of the AI lecture series today, actually at noon. It's in this building SMBB. It's up the hill past ski. And the talk is at noon. It's going to be about common sense reasoning. The speaker, Andrew Gordon, has done a lot of really cool work on how to make common sense, how to perform automated common sense reasoning, whatever that means. If you want to know, you should go to the talk. And there's also pizza at 11:10. I just want to advertise these talks a bit. This is going to be like, there are going to be 5 lectures through the academic year. We've invited big people who do like cutting edge AI research. Not necessarily machine learning, but you will see interesting hints of how learning comes into play in all of these things. Another set of talks this week, Thursday and Friday, the School of Computing organizes this annual event called the Organic Lecture Series. And we've got Maurice Henley, I can't pronounce his name, from Brown. He's like a big name in blockchains and distributed computing and stuff. And if you're into that kind of stuff, you should check out these talks. If you search for organic lectures, you get something about stuff. Just go to the talk. These are all. It's always good to go to invited talks because you get to hear what's happening around the world across, maybe not necessarily directly what you might be interested in, but across CS. So it's always good to keep an eye, keep an eye on the pulse, hand on the pulse, not eye on the pulse. More class-related things. The midterms are graded. I must say that this is the best performance in a midterm of this kind that I've had. I've taught this class 4 or 5 times now, and the midterm is not the same, but it's been of the same difficulty, and so I'm happy. If the numbers mean anything to you, you've got people, the undergrads did roughly about 75% average, the grads were about 80, and if you're, close to average or higher, you should be happy. So yeah, I'll be returning them at the end of the class today. I'll stop the lecture a little bit in advance, so that we have time to run the exams. Projects. I've still not finished reading all your project proposals. Those of you who have done the competitive, the other one, the exploratory projects, should be getting some feedback by this week. For the competitive project, there were a few questions that people asked. You should be implementing 6 different algorithms over the semester, and you could be using the same code that you use for your homework. Any algorithm that we see in class, you should implement yourself. And the good news is, if you do all your homework, you've basically almost done your project. Same rules as the homeworks. You can use any libraries that are not machine learning. There's going to be an intermediate status report that's due sometime. I forget what the date is. Sometime later this month or maybe early November. And by then you should have made 2 submissions to Kaggle, 2 non-dummy submissions to Kaggle. The one thing I wanted to mention is the data set that you have on Kaggle. I hope you had some time to look at it. The number of features is extremely large. So you should be careful with your implementations. If you're naive about it and the way you implement your vectors is just using arrays, you might run out of memory very quickly. So you should think about this, and you can use the discussion board to discuss ideas about this. There's a homework that's on Kaggle. This was, like I said, this is the homework that was supposed to help you with your midterm, but also beyond. It's due, I'd say 24th, maybe the 24th. Can someone correct me? Yeah?
On Canvas, right?
Oh yeah, Canvas, yes. You can try submitting it on Canvas, but yes, submitting on Kaggle would not help. You know, it is, I can't grade it, you won't get any points for Kaggle, nobody's happy. So yeah, it's on Canvas, and I think 24th, unless someone wants to correct me. Okay, so yeah, those are all the announcements. Quick recap of everything that I said so far. There's an AI talk today at noon. You should go check it out. There is an organic lecture, two of them on Thursday and Friday. From what I understand, the Thursday lecture is supposed to be slightly more public-facing, meaning it's supposed to be for people who are not doing research in this, and the Friday lecture is more technical. So if you want to learn about blockchain, show up on Thursday, and then both of these have receptions at the time I have marked here are the times of the reception. The lecture starts a little later. And then midterms, yeah, you have we'll get to the midterms at the end of the day. Any questions about any of these things? I'm sure. Yeah?
And this says homework 3 is due on the 23rd.
23rd? Okay, 23rd.
You can make it 24th.
Yeah, I could, but then that will only make your homework 4 shorter. So this one's better to have less time for. Homework 4, you probably need your time. Alright, any other questions? So yeah, the whole thing, the bottom thing is wrong. Homework 3 is the only part that's right, and the fact that it's due. So what we'll do now is continue with our lectures. I'm planning to do, continue with computational learning theory at least for a week, and hopefully we'll get to the end of learning theory by this week, and then pick up with more algorithmic stuff starting next week. Just a quick recap of where we were. We're talking about the theory of generalization, and we were looking at back learning, probably approximately correct learning. Just to quickly, because we've been a while since we touched this material, we defined the starting point of this style of analysis was by talking about the error of a hypothesis. The error of a hypothesis. So let's say you have some distribution over the examples D. D is fixed and possibly unknown. And you have a hypothesis H. It could be learned, it could be any function. Any function that takes an input and produces a label. For any such function, we define its error to be the probability that it disagrees with the true function. And that probability is over the distribution of the examples. And using this, we looked at the definition of back learnability. I'm not going to go over this in all detail because we spent some time on this. But generally, the idea is that we are talking about the learnability of a concept class. We have a concept class C, and we define it to be learnable for every function inside that concept class, for every distribution over the instances, and given two fixed parameters, epsilon and delta. If you have m examples, where m is polynomial in these things, 1 over epsilon, 1 over delta, and the size of the hypothesis space, if you have m examples that are sampled independently, then the algorithm L for this concept class produces some function with high probability to produce a good function. With high probability, with probability more than 1 minus delta, it will produce a good function. What does good mean? A good function is a function that has error less than epsilon. So with high probability, we can find a function that's pretty good given a polynomial number of examples. If that happens, then the concept class is said to be back learnable using this function, using this learning algorithm. Yes. This is going to be the basis of what we will be discussing for today and the next week. So I mean, at least the next class. So are there any questions about this or clarifications? In fact, on the last class before the midterm, oh yeah. So there's one other thing that we should. So notice that fact learnability talks about a notion of complexity that you may or may not have encountered in other classes like algorithms. It talks about this idea called sample complexity. What it demands, what the definition demands, is essentially polynomial sample complexity. Using only a polynomial number of examples, we can learn a good enough approximation of the true function. Of course, polynomial time complexity is also important. Polynomial time complexity is the idea that there is some learning algorithm that will, in reasonable amount of time, actually discover such a hypothesis that has that is good enough. So, fact learnability, the general framework includes both sample complexity and time complexity. We'll not talk too much about time complexity in this class because essentially that is about analyzing the algorithms, and if you want to think about time complexity, you should take the algorithms class. Or if you've taken the algorithms class, you're already experts on that. But we'll talk more about the sample complexity, and in particular, in the last lecture before the midterm, we looked at this theorem called Occam's razor, which says, which considers the following situation. You have, I don't see it written here, but I'll write it down anyway. You have a finite hypothesis class. If you have a finite hypothesis class and you have some learner that can produce a consistent. I can't talk in rights. Oh yeah, I got it right. So what that means is you have learner produces. Yeah, I can't talk in right. The learner produces a classifier that is consistent with the training set. So the idea here is that you have a learning algorithm that can produce a classifier that agrees with every example in the training set, and the question we are asking is that classifier good enough? Is that classifier going to generalize well? Is it going to have an error, a generalization error, less than epsilon? Of course, it has a training error of 0. So if you have a training error of 0, what are the conditions that will guarantee that you have a generalization error less than epsilon? And the Occam's razor theorem says that with high probability, with probability 1 minus delta, a hypothesis that is consistent with m training examples will have an error less than epsilon if you have a sufficiently large number of examples. How many examples? If m is greater than 1 over epsilon times the log of the size of the hypothesis space times plus the log of 1 over delta. Now this is called Occam's razor because of the second point here, but I'll go through this one at a time. If I demand that my error should be low, epsilon will be low. If I demand that my error should be low, this says that you better get me a lot of examples because m is the bound. If you have a lot of examples, you're guaranteed that the error will be low. So notice that this is the form the statement takes is if you have these many examples, the guarantees are met. If you don't have these many examples, maybe they are met, maybe they're not, we don't know. So the way to say this is if you have these many examples, then your error will be less than epsilon. Your error is guaranteed to be less than epsilon with high probability. Now, if you have a large hypothesis space, then learning becomes harder. Why? Because there is a log size of the hypothesis space dependency there. Similarly, if you want a higher confidence that your learner is doing a good job, then you need more examples. or the other way around. If you have more examples, then you'll have a higher confidence that your learner is doing a good job, right? So we will be exploring, this particular version of Occam's razor for the first half of today's lecture. So, any questions? Yeah.
So this does not apply to the hypothesis.
Not yet. I'm hoping to start that on Thursday's lecture. So today we are assuming that we have a finite hypothesis space and that the learner is consistent. Yeah. It turns out that a version of this, a generalization of this idea applies to that. And for example, this does not apply to perceptrons because how many linear classifiers are there? An infinite number of them, and it doesn't work. Other questions? Yeah.
You define the sample complexity to be a little bit different than the size of H.
Oh no, the sample complexity is essentially M. How many examples do you need to guarantee the epsilon delta, to give you the epsilon delta guarantee? Sample complexity is the number of examples. Okay, so today what I'm going to do is apply this result for concept classes that we all know and love and see what happens and see what is learnable and what's not. Let's start off with, so I'm going to have this thing on the top here, just so that we'll keep using that. Let's say that the concept class that we are trying to learn is conjunctions. How many conjunctions are there? There are 3 power n conjunctions, and we've seen that before. If you have n Boolean variables, every Boolean variable can either exist in the conjunction, it can be negated in the conjunction, or it can be absent. So there are 3 possibilities for every variable, every variable, and there are n of them, and all 3 of these are independent. So you get 3 times 3 times 3, so 3 power n. So there are 3 power n possible Boolean conjunctions. So the size of the hypothesis space is 3 power n, and the log of that is order of n. It's n log 3, which means the number of examples needed is essentially linear. So if you have a linear number of examples in the dimensionality, you will get any consistent learner that can produce a conjunction that agrees with your training set using these examples will have the error with high probability have no error. What does this really mean? Suppose I want to guarantee that there's a 95% chance of learning at least a 90% classifier, a classifier that whose accuracy is at least 90%. What this means is that delta is 0.05 and the 90% accuracy means epsilon is 0.1. We can plug this into the expression, and if you have 10 Boolean variables, you'll see this tells you that if you give me 140 examples that are sampled according to the true distribution, you will get you'll get a classifier that has there's a 95% chance of getting a classifier that has an error of less than 10%. Right? It does not say anything about the distribution. Keep in mind, nothing here says how the examples are distributed. All it says is, it doesn't matter how the examples are distributed. All I require is that the training and the test distribution should be the same. Now, suppose I want the dimensionality. Suppose it turns out the dimensionality goes up to 100. So the number of examples needed increases linearly in the dimensionality. So you can do the math. It will come up to be about 1,100 examples. So roughly you'll get a linear increase in the number of examples needed if the dimensionality goes up. Now, with 100 dimensional examples, if you want your confidence, you want the guarantee that you'll get the classifier to be 99%. So there's a 99% probability that you'll get a classifier that has less than a 10% error. It will cost you a little bit more examples. It will cost you from here to here. It will cost roughly the same because there's a logarithmic dependence on delta. Right? So the two things to keep in mind, first of all, here we are assuming that we know the concept class, namely its conjunction, and that we have a learner that is consistent, meaning the learner will always produce a consistent conjunction. We have such an algorithm, right? So we are not, that's not a big deal. The other thing to keep in mind here is that this particular analysis does not does not care about the distribution of the examples. There are, if you have n bits, there are 2 power n possible rows in the truth table. It does not care which of those are more rare, which of those are less rare, or more frequent or less frequent, as long as that particular distribution is the same across whenever the training set is sampled and whenever the classifier is going to be used in the future. That's the only thing that matters. So the bottom line is general conjunctions are pack learnable. So essentially what we have proved here is that conjunctions are pack learnable by simply computing the log of the size of the hypothesis class. If you remember, when we were looking at the halving algorithm, even there the log of the size of the hypothesis class mattered for online learning. If the log of the size of the hypothesis class was polynomial, halving is good enough. Similarly here, so general trend, what will happen is the log of the size of the hypothesis class tends to be an important complexity parameter. So the search space that you are searching, the log of the size of that is going to be an important thing. So the other thing to note is that nowhere in this did I talk about a learning algorithm. I never said which learning algorithm will have these guarantees. These results hold for any learning algorithm that can produce a consistent classifier. Doesn't matter which one. So this is kind of a really cool analysis. It's a way of analyzing learning algorithms without considering which learning algorithm we are talking about. It's like for every learning algorithm that has this property of consistency, you have these fact guarantees. And I don't know about you, but I think that's really cool. I'm going to give you another example, 3CNFs. A 3CNF is, 3CNF stands for conjunctive normal form. If you've not seen this, and the 3CNF consists of conjuncts, namely these things here, where every conjunct can have at most 3 literals. So you have, in this case, I just said L11, L12. L1 can be either a variable or its negation. So a 3CNF consists of a conjunction. So, this is a mistake. It will be a conjunction of disjunctions, and every disjunction can have no more than 3 things. It's a class of functions. Now I can ask, is this pack learnable? The way to think, the way to start this process is asking, in order to ask if this pack learnable, I can directly apply this result. The only thing I need to calculate is how many 3CNFs are there. Anyone wants to take a stab at it? So what we would like is, the question is, what is the sample complexity? In other words, if we had a consistent learner, how many examples do we need to guarantee pack learnability? And that is essentially calculating the right-hand side. In order to do that, we need to calculate how many 3CNFs are there.
Is there a limit on the number of total variables?
N.
Okay.
There are n dimensions that we have. Let me give you a starting point to think about this. So you have these conjunctions, right? Forget the fact that these things are disjunctions. Let's just call them. This can be Z1, this is Z2, So really what you have is V1 and V2 and whatever. It's a conjunction. Not only is it a conjunction, it's a monotone conjunction, meaning there are no negations here. So how many such Z's are possible? Every Z can be something or something or something. Someone scream the answer here. I
3
heard
to the end.
3 to the end. How did you get 3 to the end?
It looks like what we just did.
It looks like what we just did, almost. Except I cannot have an x1 here and a not x1 here. Right? If I use x1 in one of these slots, I'm not allowed to use x1 again. Yeah.
Sorry, just a quick question about how do you know that it's monotone?
Oh, because I cannot put a negation here. If I put a negation here, if I had a negation right here, the negation goes into the L11 or L12 or L13, negated becomes, by De Morgan's law, it becomes not L11 and not L2, and so I don't need to worry about it because this will get absorbed into the conjunction. So there's no need for me to count the negations. So 3 to the n is almost the right answer, except you are double counting. You could be double counting, yeah.
Is it m choose 3 and then however many for each z?
So you can have n choose 3,
Yeah.
but really a slightly better bound would be 2n choose 3 because you can have negations. So you can have xi or not xi. So you have a big pool of x1, not x1, x2, and so on. There are 2n of these, and you choose 3 of them. Of course, this overcounts things because you can still end up choosing this and this, but this is a tighter bound. So really, the answer is, you might disagree. I'm going to erase this, but you might disagree that this is too loose, but really it is 2n, choose 3, and you have how many? So you have number of these. Is this, and I'm going to do something really annoying. I'm going to call this roughly order of 2n cubed. It's it's a little bit off, but it's in that order of 2n cubed. And then with these things, we need to produce a monotone conjunction, and so that is every one of these z's can either be present or absent, so you get 2 power 2n. This is all we go. So the number of 3 CNFs is 2 power 2n cubed, order of that. I want you to revisit this and kind of rederive this by yourself because it's useful party trick for the kind of parties that I go to. So the number of conjuncts is this is not right. So it is order of 2 power 2n cubed. Now can one of my TAs remind me to fix this later on? So that means that I've essentially written the proof here. Okay, the number of conjuncts is order of 2 power 2n cubed, and what we have is a conjunction, a monotone conjunction of these things. So you get the size of the hypothesis class is 2 power that quantity. So the log of that is order of n cubed, which means this thing here goes here. The sample complexity is polynomial in the dimensionality, right? Because it's polynomial in n, cubed is still a polynomial, and then the epsilon and delta stuff comes for free because it is already polynomial in 1 over epsilon, it's already polynomial in 1 over delta. So the sample complexity for learning a 3CNF is cubic in n, it's polynomial in 1 over epsilon, it's polynomial in 1 1 over delta, so 3 CNFs are packed learnable. Question? So what this says again is if there exists an algorithm that can take a data set and produce a 3CNF that is consistent with m examples, and if the data set had those many number of examples where the log of the size of the hypothesis class is replaced with n cubed roughly, then with high probability, with probability greater than 1 minus delta, that particular 3CNF that your consistent learner has produced is going to have an error less than epsilon, meaning it's a good enough classifier. It does not say anything about the existence of such an algorithm. It only says, if you have a consistent learner, this is good. Now, the most important part of all of this is, assuming that you know how to get to that expression, the most important part of this whole thing is counting the number of functions. Once again, it's counting how many such functions exist. Of course, we still need to find an efficient algorithm. If there exists an algorithm, all this says is this algorithm is going to be good. I've said nothing about which algorithm that is, and I'm going to leave that as an exercise. Think about how you invent a learning algorithm that can take a data set that is produced with a 3CNF and will produce something that is consistent. I'll leave that as an exercise. You can come talk to me afterwards. Let's be more ambitious. So what we started off with just conjunctions. And then turned out they were packed learnable. Then we expanded the class to be 3CNFs. They also turned to be packed learnable. Maybe everything's packed learnable and the whole definition is useless. So let's be ambitious and go to arbitrary boolean functions. How many boolean functions are there with n variables? I hear murmurs, but yeah.
Is it 16 to the end?
It's not 16 to the end. I don't know how you got that, but it's not 16 to the end.
2 to the 3 to the n?
Close. It's 2 power. This was essentially the reasoning behind this. I probably mentioned in the second lecture of the class. If you have n variables, how many rows are there in the truth table? That's 2 power n. Now, a function is completely defined by the value of the function. The Boolean function is completely defined by what value that function takes for each particular row in the truth table. So I can put for every row in the truth table, the function value can be a 0 or a 1. There are 2 power n rows, so there are 2 options for each row. So 2 power n. So there are these many Boolean functions, which means log of the size of the hypothesis class is still 2 power n. It's exponential, which means general Boolean functions are not packed learnable. Why? Because the sample complexity is exponential. In order to guarantee that even a consistent learner is going to be good enough with high probability, you need an exponential number of examples, which we are not going to have. Exponentials become really big, really fast. If you have 100 variables, 2 power 100 is an unreasonable number. So general conjunctions are not packed learnable. So at least the definition is not vacuous. At this point, I'm going to just throw out a list of functions: KCNFs, K cross CNFs, KDNFs, KTerm. These are all different kinds of Boolean functions that have been studied a lot. Those of you who may have taken models of some sort of discrete math, you may have seen some of these in discrete math class. I'm just going to talk about 2 of these, and I'll leave the rest of them as for you to look at later. KCNFs are basically like conjunctions. Like KCNFs are a generalization of 3CNFs. We just saw 3CNFs, right? Instead of 3, you have K. So you can have a conjunction of K, conjunction, where every entry in the conjunction, every element of the conjunction is itself a disjunction of at most K things. That's a KCNF. A K-term DNF is a disjunction of at most K conjunction. You can think about how these things are complicated. Now, turns out all of them are path learnable. If you want something to keep you busy, try to count the number of functions. They kind of follow the same sort of reasoning where you replace the big outside conjunction, the same thing that we did in the 3CNF. Yeah, exactly. All of these have polynomial sample complexity. What that means is, for each of these functions, if you can find a hypothesis that agrees with the data, and you have a polynomial number of examples, all of them will have a different polynomial. The first one, for example, KCNF, the polynomial will be n power k. It's a big polynomial, but still, polynomial. If you have a polynomial number of examples, and you have a learner that produces a consistent function of that class, then you will, with high probability, that function is going to be good enough in the future. Now consider a two-term DNF. A two-term DNF is something that looks like, I'm going to write D1 or D2. Just two things where each of these can be a disjunction. So this can be something and something, and then this can be another one of those things. So it's a big conjunction or another big conjunction. That's a two-term DNF. So I just said this is path learnable. It's just two of these things. Either this is true or the other one's true. I should put a or. Right? So I argued that this is path learnable. Yeah.
This might be a stupid question, but I'm just wondering why we are talking about boolean functions like CNF and DNF, because in the real world,
That's
the
a
hypothesis type is usually not the boolean
no.
function.
That's a great function. That's a great question. So if you didn't hear it, the question was, why are we talking about these classes of functions when in real life we never have to use them? No, that's a perfectly valid question. Two reasons. One, these kinds of functions are easy to analyze. The other thing is, it turns out even with these simple sort of things, we run into problems. In fact, we're going to run into one problem right now. Even with simple kinds of functions, we run into problems that do manifest themselves with real functions. These are like these toy problems that we can, study and argue that life is not perfect. That's one thing. The other thing is, historically, these have been the ones that were first analyzed. So there's a reason why the theory for all of these is so well studied. So we have that Boolean function there. D1 or D2, where everything is a conjunction. So the question, which is going to lead into it's a trick question, is suppose I know that the concept is a two-term DNF, and I want to invent a learning algorithm. What hypothesis class should I use? Since it's a trick question, you can give me the obvious answer and get it out of the way. Yeah?
Two-term DNFs.
Yeah, that's the obvious answer. If you want to learn that thing, you better search that space. That seems like a reasonable thing, especially because it's path learnable. It turns out, even though the sample complexity is polynomial, there exists no learning algorithm that can learn a two-term DNF by searching the space of two-term DNFs. If your search space is only two-term DNFs, you will not find a function in polynomial time. So finding a consistent two-term DNF with by searching over a space of two-term DNFs is NP hard, which means, so NP hard is just saying that it's not polynomial, it's not tractable, which means that this concept class is not efficiently path learnable, it's only path learnable, and we do see this a lot. So what this is kind of an annoying thing. We have a function, we have a set of functions. I know the sample complexity, the polynomial sample complexity says, I know the information exists in a polynomial's data set, in a small enough data set, for me to find the function, find the right function, or a close approximation of a good enough function. But there is no search procedure that can actually search that space and return such a function in a reasonable amount of time. But it turns out, and I'm not going to talk about this in detail, every two-term DNF can be rearranged as a KCNF. So if and there is a construction here, you can look at it later on. What this means is, if this is a class of two-term DNF, and this is a class of KCNF, every two-term DNF is contained in a KCNF. And we knew there was which means we can use our learner for KCNFs, which was efficient, which I left as an exercise for you to find, to learn this thing. So the weird thing is, if our search space, so let me give you so suppose you have a concept class, C, this is your two-term DNF, and searching this concept class is computationally intractable. So the solution is take a bigger hypothesis class which contains this thing, and weirdly, even searching this bigger space is efficient. Does that bother you? Okay, I've never been able to get used to it. So we have a class of, but it does. This sort of a thing happens a lot in multiple kinds of discrete problems. If you have a discrete, this sort of weirdness is just apparently common in combinatorial problems. So if you have a class of just to restate what I just said, if you have a class of functions, this class of functions, I know that the true function is inside the red circle, but if I search inside the red circle, I'm not going to be able to find the answer in a reasonable amount of time. Instead, I search the larger circle and somehow I get the right answer. So this happens, and it turns out this is not the first time we are seeing this. We already saw this before. Essentially, this is about representation. Sometimes a concept cannot be learned using one representation, because using that representation for learning is inefficient. However, you could use a different representation to more efficiently navigate the search space, and the other representation contains the one that you care about. We've already seen this before when we looked at boolean functions and disjunctions and conjunctions and all those things. You could keep inventing new algorithms for all of those things, or if your boolean function is linearly separable, might as well just use an algorithm that works for linear classifiers, and you're going to get the right answer. So that goes back to your question, which is, why do we care about these things? It turns out these are all interesting classes of functions, and it turns out we don't need to care about them, because we can use other learning algorithms and we are guaranteed to be right, provided it contains the class of functions we care about. But this is a weird thing. It used to be the case that for every class of functions you had to invent a new algorithm, but now maybe you don't need to. Questions? So computational complexity is an important thing. That's the lesson here. There are no questions. I'm going to march on. There are other kinds of negative results. There are other classes of functions that are not learnable. And negative results can take two forms. You can have a computational complexity problem, namely a certain class of function cannot be learned because it's too inefficient. There is no algorithm that can efficiently learn it. Usually, the standard proof for these things, and we're not going to prove a single result of this kind. I'm just going to give you a flavor of this. A standard proof of these things says this concept cannot be learned unless P equals NP. And that basically says it can't be learned, if you ask most people. The other kind of a result that we can have is an information theoretic result, which says the concept class is so rich that only a polynomial number of examples are not going to be enough to distinguish two functions. We've just seen a proof of that kind, like for general conjunctions, for general boolean functions. Basically, the proof says that you cannot learn functions of that kind using only hypotheses of that kind. Just a few things that cannot be learned. K-term DNS cannot be learned because they are computationally expensive. That's the example that I just said. A lot of interesting neural networks are essentially unlearnable, and yet things seem to work. That's something that is actually a failure of this theory. The theory says neural networks should not be learnable, and in practice they seem to be working perfectly fine. So today, one of the big open questions in machine learning is, what is the theory that there seems to be clearly some gap between what the theory says and what seems to be happening in practice, which suggests we need new theory or a refinement of the theory. There are other Boolean functions that are also not learnable. You can look them up. These are all in complexity point of view, from the computational point of view. From the information theoretic point of view, arbitrary Boolean functions cannot be learned. That's the thing that I just proved. Those of you who are taking models of computation or have taken models of computation, you may have seen finite state machines or context-free grammars. They cannot be learned. And yet, we seem to be doing surprisingly well with in natural language processing by actually learning context-free grammars. So once again, the theory seems to come short. This is just a point about, the negative results that we have are all worst-case results, and in practice, things seem to be okay, which suggests that our theory needs a bit of refinement. Okay, so this is essentially the end of the list of examples that I wanted to present. Are there any questions before I move to agnostic learning?
So you mentioned that it might be easier to learn something in like Boolean functions instead of linear threshold.
Right.
But that's only if the function is linearly separable.
That's right.
So it's not always the case. Like,
Oh no, absolutely. That's absolutely right. I mean, it's not always the case. If you can find a function class that is strictly larger, and the larger class admits an efficient algorithm, you might probably be better off implementing that, because then you get more. But you need the strict containment. Yes.
So in all the cases where we're using the perceptron, we know that it's linearly separable.
Or we assume it's linearly separable. We know nothing, right? I mean, when you get real data, we just hope it's linearly separable. Yeah. Yeah.
So, okay, just to summarize, since we know that our function is a linear, in the perceptron example, we're assuming our linear threshold unit is, so it encompasses this concept class of linear separable functions. So it's analogous to this in terms of saying, like, we know that's maybe like a larger concept class that we need to cover, but it's okay because the perceptron can learn any linearly separable concept
Basically,
class.
yeah,
Okay.
that's right. Except some of these classes of functions are so large that nothing's going to work. Like arbitrary Boolean functions, there is no discrete function that is larger than that. So we are stuck with that. Alright, so now I'm going to move to agnostic learning. We just looked at these positive and negative learnability results, and so what we've seen so far is we've looked at the general setting for batch learning, and we've asked this question of how good will a classifier be if it is consistent on a training set. There are a few assumptions that we made. That one of them is that for this consistent distribution assumption, namely every example is drawn IID from a fixed, perhaps unknown distribution over the examples, but the important point is they are fixed. And then the second one is that the learner produces a classifier that is guaranteed to be consistent with the training setting. Now, is the second assumption reasonable, or is it even needed? Is it possible that your learner doesn't perfectly classify the training set? Think about your homeworks, for example. Right? You do get learners that seem to be okay, but they don't get 100% training accuracy. So, we've assumed that the learning algorithm can find the true concept. So, what that means is a picture like this. You know, your hypothesis space contains every concept. But what if your hypothesis space does not contain every concept? Maybe your concept lies inside the red circle at the bottom, and for whatever reason, for convenience, or because you have the code lying around, you're searching in a different place. Worst case, maybe it does not overlap even. This could be C, and this could be H. They have no common elements, and there might be pragmatic reasons for doing this. So, what if we are trying to learn a concept using hypotheses in this function, in this class H, but we have no guarantee that the true function is in our hypothesis space. C is not a subset of H. This setting is called agnostic learning. The learner is agnostic to whether the true function is inside the hypothesis space or not. This is a more realistic setting, because this is the kind of setting that we actually play with. So, can we get sample complexity bounds in this setting? That's the question. The first thing I want you to realize is that in the setting for in agnostic learning, we are no longer guaranteed that the training error is going to be 0, right? Because it's possible that the true function is not even contained in the class in the set of functions that we're searching for. So there's no guarantee that the training error is 0. So what we can do is to find a classifier that has low training error. Maybe just find a classifier that has the lowest training error. Remember, the training error, we call that error S, is simply the fraction of examples in the training set that are misclassified. So we can maybe invent a search procedure that finds H that has the minimum such error on the training set. Is that good enough? Is that going to be a good classifier? Maybe. What they really care about is not the training error, but we want generalization. We want some sort of a guarantee that connects the training error to the generalization error. If we could do that, then we've essentially solved the problem of agnostic learning. If we can somehow say that a classifier that has low training error on a large enough set of training examples is going to be good enough in the future. If you have, so the kind of result that we are looking for is, if you have a large number of examples and you find a classifier that has a low training error on this extremely large set of examples, it's unlikely that this is going to be a bad classifier because the number of examples you have is big enough. So what we need is some mechanism to connect the training error to the generalization error. The generalization error is the probability that the classifier makes a mistake. In order to do this analysis, we're going to use tail bounds. How many people have seen tail bounds before, like Markov's inequality or Chebyshev? Some small fraction, and I'll vaguely introduce these things. You should probably go back. Very loosely, we are asking how far the tail bounds let us ask the question, how far a random variable can be from its mean? How far what's the probability of the random us finding ourselves in the tails of the distribution. Just a quick example. Imagine that we are tossing a coin, and we don't know the bias of the coin. The coin could be heads. The probability of the coin being heads or tails, let's say we don't know what it is, and we want to get an estimate of the probability of heads. We toss the coin many times, and we count the number of heads, and we divide by the number of tosses we had, and the fraction is an estimate for the probability of heads. Now, suppose you toss the coin 10 times. You get some fraction. Let's say you toss the coin 10 times and you get this fraction. So, number of tosses, I'm calling that m here, and this number of. So, let's say you toss it 10 times and you get an estimate of say 0.7. So, you got 7 heads. Let's say in another experiment, you toss the same coin those many times. It's a sad life if you toss a coin those many times, but and you get an estimate of say 0.63. Which of these is more believable? 0.63 because you have more evidence in some sense. So we can ask, so one thing that we know is that as m goes to infinity, we will get to the right probability. That's the law of large numbers. But how fast does it go? How fast does the gap between the fraction and the true probability shrink as we get more and more tosses? In order to answer this question, we can appeal standard tail bounds. Some of you may have seen Markov's inequality. It says it asks what is the probability that a random variable is greater than some a, and it says probability that it's greater than a is less than the expected value of that random variable divided by n. Chebyshev's inequality is a refinement of this. That is, it's bounding the probability of how much a random variable, the difference from the random variable to the mean can be more than a fixed number of standard deviations. Sigma is a standard deviation. It says you can't be too far off, and it doesn't matter what distribution you have. But neither of these are useful for us because what we want to bound is the training error. How far can the training error be from the generalization error? The training error is essentially like the number of times you made a mistake divided by the number of training examples. It's like the coin toss example. So it's essentially the sum of random variables. So what we care about is bounding the sum of random variables and also asking how fast does it approach the true error. Neither of these help us here. It turns out what we need is something called Huffing's inequality. This is actually a fun inequality to prove. You should try that out. You can prove it using the other tail bounds. But I'm not going to talk about it now. I'll just give it to you as let's treat this as a given. Huffing's inequality tells us how much can the sum or the let's say a sum of a random variable differs from the expected value. So to ground this in the coin toss example, say you have the expected, say P is the expected mean. For coin tosses, this is the probability of getting heads. So, and we are asking what is the probability that P is greater than the empirical mean. The empirical mean is the dividing the number of heads by the number of trials. What Huffing's bound says is what's the probability that the empirical mean is more, the true mean is more than the empirical mean by some number epsilon after m trials. And what it says is that after m trials, the true mean will be pretty close to the empirical mean, and not just pretty close, if you get more trials, you'll get closer at an exponential rate. So it gives you the it also quantifies the rate of convergence. So it says if you toss a coin m times and you care about the probability of heads, the probability of, so think of this as probability of heads is greater than number fraction of heads divided by m plus epsilon. The probability that this is true is less than that number. So it's a very rare event that your true probability will be very far off. Questions before we start using this? Yeah?
Would we be expected to prove this inequality on an
No.
exam?
But it's good for life.
Okay.
What's the epsilon?
Epsilon is some parameter. Epsilon is saying it's the error here, if you want to think about it that way. Epsilon is saying what is the probability that you'll be, it's a gap between these two things, and like we are just asking what's the probability that the true error, the true mean is more than the empirical mean by some epsilon. You see that there's an epsilon square there. As epsilon gets smaller, this goes really, really close, which means that you will be really, if epsilon is say 0.1, you're basically fine. Well, if 0.1 is still, epsilon is say 0.001, you're basically fine because that you have an epsilon square and you're almost, I said that the other way around actually, because there's a negative. Never mind, forget that. Forget the last 30 seconds. Yeah?
Are these three inequalities that we just went over like standards or like the grade of your data? So you say like this is Markov.
No, so these three inequalities are just statements about probability distributions. It has nothing to do with data, it has nothing to, well, it does of course, but it has to do with any probability. It's not about machine learning per se. It just says, given any random process, given a set of trials, what's the probability that the empirical mean is going to be too far? It could be anything. It just so happens this is like the perfect tool for analyzing learning because the empirical mean is like the error of a hypothesis, the true mean is like the true generalization error. It just so happens that these are the perfect tools. But they have, did that?
Yeah.
Yes?
What is E?
E? E is the number E, 2.71 something. Did you have a question?
So what if the true mean is on the other direction?
Oh, right. So this is just one of the directions. The general Herding's inequality has there are two inequalities. So there are like two versions of this. I'm just showing one of them because that's the analysis. That's the one that I'll use for analysis. Yes, of course, it could be less than. In fact, the actual Herding's inequality takes the form probability that P minus P bar is greater than epsilon. Alright, so I can go one. So let's go back to agnostic learning. I'll just start this process and then continue again on Thursday. So the somewhat mind-bending part of this is the idea that we are going to consider the generalization error as a random variable. Now, the reason that's mind-bending is the generalization error itself is a probability. It's a probability that your classifier makes a mistake. So now we are going to treat the probability as a random variable and talk about the probability that probability is close to something. It's not that complicated. So the empirical, the generalization error is probability of, I just want to write this, probability of error. It's the true probability of error. think of it as like the true bias of the coin. There's some coin and we don't know what the probability it gives you heads. This is the empirical estimate. So think of this as number of errors divided by n. Very much like the coin toss kind of situation. So we can directly apply Hutchinson inequality here. We can ask, what's the probability that the true error is more than epsilon away from the empirical error? Because the empirical error is something we can measure. We can calculate the training error and we can ask, what's the probability that the true error is more than epsilon away from that? We can apply Hutchinson inequality. We can say, ask, what's the probability that the true error is more than epsilon away from the training error? So this is really like your the bias of the coin. Let's call it P, and this is number of errors divided by m. And without too much thinking, Hutchinson inequality directly tells us that this is less than e power minus 2 m epsilon square. This is literally a direct use of that result. But this is for a particular hypothesis. There's this one function, and the probability that the true error of that function is more than the empirical error is this much. But we don't, during learning, we are exploring every possible function, and we want to find one of them. So, we can ask, so this is the probability that a single hypothesis is more than has a training error that's more than epsilon away. We can do exactly the same thing that we did with what do you call that thing? The previous case with Occam's razor. We want to find the best one of all of these h possible things, so we can apply union bound. The probability that there exists a hypothesis whose training error is more than epsilon away is the size of the hypothesis times this thing here. Now, this is the same union bound game that we keep playing in machine learning all the time. This is like a loose upper bound. If you're uncomfortable about union bound, I just looked it up last night. It turns out the Wikipedia article is not terrible. I was kind of concerned that I had to spend some time introducing it, but I just wanted to see if there is something out there that is well written. It's okay. So I recommend you look at it. So what we have is the probability that there exists a hypothesis whose true error is too far from the training error is less than the size of the hypothesis times e power minus 2 m epsilon square. So this is what we just had, and we're going to do the same thing before. Now, this situation is bad. This situation is bad because what if the hypothesis that causes this thing to happen is the one that our learning algorithm returns? Maybe our learning algorithm returns some hypothesis, let's call it h, and that is the one that has the true error that is too far from the generalization error. We don't want that to happen. How much do we not want that to happen? We want that to be less than delta. But instead of making that less than delta, we can put this, the right hand side, less than delta, or yeah. If this quantity is less than delta, then obviously the thing in the box is less than delta, which means bad situations are not going to happen, or are going to happen with a probability less than delta. So we have if the thing in the box is true, then any classifier that our learner returns is going to be reasonably good. Now I can rearrange this thing. At this point, it's just going to be algebra. I take log on both sides and just rearrange. So log size of the hypothesis minus 2 m epsilon square is less than equal to log delta, and then you shuffle things around and you bring m to one side, and you get an expression that looks extremely similar to what we saw before. If the number of examples we have, m, is more than 1 over 2 epsilon square times the log of the size of the hypothesis plus log of 1 over delta, then this quantity is going to be less than delta, which means no matter which hypothesis our learning algorithm gets us, that it's the error of that, the true error of that hypothesis is not going to be too far from the training error. Keep in mind, this does not say that the true error of the hypothesis is going to be small. It only says that the training error is a good estimate of the generalization error. Maybe the training error is really bad. Maybe the best classifier that we can find is lousy, but that's life. All we can go by is how bad is it in comparison to the training error. So, there are two ways of interpreting this, and I'm going to kind of, without proof, give you the second one also. But the first one is just talking about, there's no commitment about the true function being in the search space or not. Because if it's not in the search space, our classifier, even the best classifier that we can find, is going to have some error. And what this statement guarantees is, if you have these many examples, then there is, with high confidence, with confidence more than 1 minus delta, your true error is not going to be more than epsilon away from the training error, if you have these many examples. That's one interpretation. Yeah?
In that second point, is the first training error supposed to be true error, or is the second training error supposed to be true error?
Sorry? Oh,
Yeah.
yeah, this is true. Thanks. Yeah, that makes more sense. Yeah. Yes. This is one interpretation of this result that we just proved. Notice that the epsilon here is no longer the error of the classifier, but it's the difference between the training error and the generalization error. How much worse will the classifier be in the future than it was during training? This, once again, we have the size of the log of the size of the hypothesis space that comes in. So this is an Occam's razor argument. This is the Occam's razor argument for agnostic learning. Once again, this suggests you should prefer smaller function classes. There's another way of interpreting this. We get a generalization bound. It says, how much will the true error deviate from generalization error? And I'm not proving this in detail. There's a subtle argument here. Basically, it says, if you have more than m training examples, then the generalization error will be the difference between the generalization error and the training error will be less than some point. So generalization error will be not too much worse than the training error, and how much worse is it? It's the thing in the bracket. So we've seen two things so far. We've seen Occam's razor when the hypothesis space contains the constant class. That's the one that we saw before. There is an epsilon dependency here in the denominator. We've also seen Occam's razor for agnostic learning. The hypothesis space may not contain the true concept, but we can still get some sort of a bound. If you have these many examples, life won't be too bad. Both these statements basically say, if you have these many examples, then with high probability, your classifier will not be too much worse than what it was during training. In the case above, what it was during training was perfect. There was zero error during training. In this case, there was some error during training. In both cases, here because we are in a more difficult situation, there is a square dependency in the denominator. So, the bottom line is the learnability of a concept depends on the log of the size of the hypothesis class, both here and here. So, question. Have we solved everything? Do we have all the theoretical tools we need to analyze, say, something like perceptron, the batch perceptron? What's missing?
Still finite hypothesis classes.
Still the finite hypothesis class, and if you try to measure the log of the size of the hypothesis class of linear classifiers, it looks like infinity. It is infinity. And that's a trivial statement. It basically says, if you have an infinite number of examples, things won't be too bad during test time. Of course it won't. If you have all the examples that can possibly exist. So the theory is only valid, everything that we saw so far is only valid for finite classifiers, and on Thursday we're going to start looking at how we can extend this to infinite classifiers. I'm going to stop now and start handing out the exams. Before you guys all get out, I just want to point out there are many of you in this class. So please organize yourself by last names according to this and find the person.